Just some reminders about chapter one. The first problem that you come to in chapter one, the first two problems rather, is the tangent line problem and the area under a curve problem. And so remember, the tangent line touches at the 2 points, which is a secant line, and they continued to get these points closer and closer together. When the points were infinitely close together, or that distance was approaching zero, then you found the tangent line. And so basically, they use the regular old slope equation here, and they just did it as that distance approached zero. And then again, the area under the curve, they started with something that they know, area of a rectangle, which was an estimation. You can see it left spots. The more rectangles they had, the closer they got to the actual area under the curve. And so they moved this number of rectangles to infinity, and then they got the actual area under the curve. And again, a known pre-calculus concept with a limit theory concept in calculus to move it to what is eventually going to be derivatives that we do to find these slopes and areas. One of the first ways that you found limits was estimating it numerically. You are given a function, you create a table. The limit that you're trying to approach, or the x value c that you're trying to approach, is always here. You're going to go tiny distances away on the left, the same distances away on the right. You're literally just plugging these in and getting your y values. And you can see that the y value is approaching 2 on both sides. So the limit here then would be 2. All right, so the reasons that you could have a limit that did not exist, an overall limit will not exist if that function is approaching different numbers from the right and from the left. Remember, to have an overall limit, they have to be going towards the same thing. So if you have a function that is going this direction and then this direction here, we would not have a limit right there. Increases or decreases without bound. So that is it approaching infinity? Remember, for real numbers, infinity does not count as a limit. So if it increases or decreases without bound. And then the third thing that can cause a limit to not exist is if it oscillates. So if it's pinging back and forth between two numbers, you will not have an overall limit. So then the formal definition of limit is, let f be a function defined on an open interval containing c, and it can be undefined at c, that's fine. Um, the limit as x approaches c of x equals L means that for every epsilon greater than zero, there is a delta greater than zero, such that, and you have zero and delta here, x minus c, remember c is the number that you are approaching, then you're going to have an epsilon where the function minus the limit is within that range. And so what they're telling you here is the delta represents the range that the C value. So I can get within these ranges of C and I am close enough. And if I get close enough or in these ranges, then my limit will also fall close enough and it will be in the epsilon range. So how do we actually apply this? If they gave us something like this, you are going to say, well, I need my limit to be within point one of my actual limit. My actual limit here, if I were to approach, I think right now they're approaching one. So if my actual limit here, you can easily solve this, is 1/1. My actual limit is 1. That means I need to go no more than 1.1 in the y and no less than 0.09, which means that I need to figure out how far away I am from that. And so you can literally just solve for that x value. You can say, well, 2 minus 1 over x needs to be less than 1.1 and greater than 0.9. So what x values would that create for me? And then just solve for x. So solve for this group right here, and then solve for the other group right here, and you will see that you have two values. Always pick the lesser of the two values because you have to be within the range. And if you pick the higher one, it may be too big. Right, just some basics of limits. Remember, the limit of any constant is just the constant. The limit of x, you're just plugging that in. Again, x to a exponent, you're plugging in. Scalar multiplication, you can multiply limits, you can add limits, you could subtract limits, multiply, you can divide as long as your denominator is not zero, and you can take a limit to the power. These proofs are explained in the details in that Google Doc that I have, but these are your basics of your limit. So when you are finding limits, you want to do the path of least resistance. Always try to plug it in. If it does not cause a problem, plug it in and solve. That is your limit. If you cannot plug it in, let's say you have a zero in the denominator, then you want to first see if you can factor and cancel out your problem. If you can factor and cancel out your problem, then you can just plug it into your simplified. The last thing that you need to look for if you cannot plug it in and cannot factor is, does it have a radical or something that I can rationalize? Remember, to rationalize it, you're going to multiply the top and bottom by the conjugate of whichever piece has that radical in it. It will get rid of your problem. And then once you've canceled out your problem, again, just plug it in and you have found your limit. All right, so one of the theorems in this chapter is the squeeze theorem. The squeeze theorem states that if you have three functions, f of x is between two other functions, h and g, for all x's except maybe c, which is what you're trying to approach. Um, and you have a limit of h and g that are the same at that c. So we have a function that falls in between two functions that have the same limit at the point that we're trying to get to. Then, if that function in the middle has a limit, it will be equal to those other two functions limits, which is the same. So we have an upper function, a lower function. This is actually the function we're trying to find the limit for. These two functions have the same limit at the point we're trying to reach, but our actual function is undefined at that. We can actually use these two functions to say, hey, all three of their limits are going to be the same. And the two main ones that you learn in the squeeze theorem are sine x over x as x approaches zero, that's going to be one. One minus cosine of x over x as x approaches zero is zero. And sometimes you'll see other functions or a scalar of one of these functions, and you're going to use them to then solve. All right, so some limit existence or continuity existence issues here that you come when you are doing continuity. So section 4 is continuity, and you're going to see three things that have continuity problems. And so the first one is that maybe the function is not defined at a specific point. And so if it's not defined at a point, then it is not continuous on this. Maybe it is defined, but it breaks like a jump. And so you can have a jump that's not continuous. Well, maybe it is defined at all these points, but it's not the same. So this is also discontinuous. We come up with our continuity definition. The definition of continuity says that in order for it to be continuous, all three of these conditions have to be met. The function has to be defined at C. The limit has to exist at C. And the limit at C has to equal the function defined at C. So the limit at C has to equal what happens when you plug C into the function. If that happens, then it is continuous at C. Now, in order for it to be continuous on an open interval, it has to be continuous at every point in that interval. In order for it to be continuous everywhere, just like it sounds, it has to be continuous from negative to positive infinity. So definition then on a closed interval, a function can be continuous on a closed interval if it meets all of those requirements um, for every point in that closed interval, which means it could be a discontinuous function overall, the real number spectrum, but it could be continuous on certain intervals. This definition also mentions continuity from the right and the left. Remember, um, from the left means coming from this direction. What does it look like your y is approaching? And from the right means from this direction. What does it look like y is going to do? And so you can have individual right and left hand limits. The only way you have an overall limit is if these two are the same. If they're not the same, you do not have an overall limit. You only have right or left handed limits. So properties of continuity, once again, continuous functions can be multiplied by a scalar, they can be added and subtracted, they can be multiplied, they can be divided, and again, not by zero. The intermediate value theorem is states that if f is continuous on a closed interval, and that the start when you plug in the beginning number, it does not equal the ending number when you plug it in. So remember, these are your y values at a and b, and k is a number that falls in between those y values. Then there has to be a number that falls in between your x values. What they're saying is if it's continuous and these are not the same numbers, meaning b gives you a different y than a, then if there is some number in between the y values, there has to be a corresponding x number in between the x values. That is all the intermediate value theorem is saying. And you can see how it works for this, but it does not work for that because this is not continuous. Your initial if statement is not met here, so you can't assume the rest of it.